Okay, we are recording here. Wireshark WCNA number 6. We're going for 70 minutes, covering two chapters, chapter 15 and chapter 16. Just make sure you've got your Wireshark on. You don't have to have anything capturing just yet. So DNS, very important, and also ARP is very important. Thing with DNS is I don't know how many job interviews you guys have been to, but for your basic tech support and also lower level network engineer jobs, a common question will be, how does DNS work? And they're probably not going to ask you, that's a pretty broad question, how does DNS work? What they're probably going to ask you, or the way they're going to ask you, is when I type in CNN.com into the web browser, what happens? You hit enter, what happens, right? Where does that DNS go? How does your computer know what server it hits? Stuff like that. How does the DNS server get that information for CNN.com? Is it cached? Stuff like that. That is a very common question, especially for tech support guys. So just something to keep in mind. That, and also another common question is, what happens when you send an email, right? So I got that question when I started at NetZero. The way it was actually worded was, old lady calls up and says, I sent an email to my son, or not my grandson. Why didn't it reach him? And you ask the question, well, what email address did you send it to? My son at internet.com. And so you have to explain it to the lady why that doesn't work. So, all right. DNS, pretty cool stuff. Basically, the plumbing of the internet. It's how easy names like CNN.com, ESPN, eBay, that type of stuff is used. How you're able to type those in, and then you get to an IP address. So you generally can't remember 207.63. Whatever, whatever. And so it's easier to remember CNN.com. But there needs to be a server that translates all that information. Right? And I just realized I need to share a screen. Okay, there we go. Screen is shared. Okay, so it translates easy names into IP addresses, and of course there needs to be a DNS server. For most cases, if you're at home or you're on DNS, you're on DSL or cable, you've got a router, probably a Stinksys or some type of router, and that is acting as your DNS server. Okay, so we can check that DNS server. Hopefully this isn't anything new to you guys, but if you go down to command prompt, and hopefully all of you guys in this room should know that. If you go down to command prompt and if you're on Windows, you do ipconfig/all, you're going to get that information. So ipconfig/all, and then you scroll up to the appropriate connection. In my case, you notice I've got a lot, and that's what happens when you start running VMware and VirtualBox. You've got all these you got all these virtual connections, and you just have to hunt down to the right one. So wireless LAN controller, my DNS servers are 172.18.2.2, and I've got a backup one, 172.18.2.7. Right? If you're at home, it's probably going to be something like 192.168.1.1, 10.1.1.1, 172.16.1.1, the very common Linksys gateway IP addresses. So your gateway and your DNS server will probably be the same. Okay. So if you have yours set to all 8s, then that has been manually entered in. That's the very common Google one. Yeah, that happens quite a bit too. That one should never fail. Now, for some of you guys, you may see, let's see here. If you do a ping to CNN.com. So ping to CNN.com, you get an IP address back, 157.166. If you ping to www.cnn.com, you're going to get something a little bit different, 157.166. And if you ping something just off the wall weird.cnn.com, so just type in a bunch of text.cnn.com, you're going to get something, it's basically saying, duh, what did you type in? Now here at Panda and on most corporate networks, you probably have a DNS suffix. Here it's pandarg.com. So like we have a server here called Jaguar. I should not be able to ping this. This is on guest. Yeah. So if I was on the wireless internet, I'd be able to ping it if I ping Jaguar. And Jaguar's full name is jaguar.pandarg.com. But what happens here is in my DNS settings, I've got a DNS suffix, and this comes from the DHCP server. It's going to add in .pandarg to everything. So this will usually happen if you're on the corporate network. If you're at home, probably nothing's really added to your DNS name. So if you ping like Bob, it's just going to try to ping Bob without any ending after that. All right. You can just minimize that command line window because we're going to come back to it when we play with Wireshark. So most common way of using DNS, very simple. You type in a name and you get an IP address. Everything happens in the background. You don't need to worry about it. That is what's called an A record. That's probably like 99.9% of the time the way you use DNS from your user perspective. Less common stuff is reverse lookup that changes the IPs and the names. Very often used for spammers or trying to find spammers to see if something, a particular email address is legit. So reverse lookup. I don't know how many of you are sysadmins for big companies and you need to whitelist email addresses. This happens every day here. Someone wants to email us and we have something called Mail Marshal that blocks it. So there's all types of different email protection programs, but basically what happens is it thinks that it is spam and looks it up in reverse lookup and something doesn't match and it will block it, right? So then you have to call the guy, you have to look it up on sender base, all that good stuff, and make a determination whether to allow it in or out. So reverse lookup. Usually don't deal with that unless you're a sysadmin or you're a spammer. The way spammers do this is spammers will falsify the reverse lookup and make it look like something different, like facebook.com or something like that. Also less common that you won't see as an end user is zone transfers. Zone transfers are the way DNS servers transfer information between each other. Okay, so think of it as a basically database transfer. So when you go to CNN.com, you're actually going to not CNN.com itself, but you're going to some server at CNN.com. So something like www.cnn.com. Sometimes you may have gone to a server and you've seen www1, www2, www3, so on. So that's probably some type of load balancer, multiple servers behind there, behind like a F5 or something. Okay? But the C name is the actual true name, the real name, and that's going to be just CNN.com, eBay.com, something like that. Okay. So dissecting the DNS packet, there's going to be quite a bit of information inside there. Once we start looking, going on hands-on, you'll see that there'll be transaction IDs. Transaction IDs are what keep the DNS server replies and responses in sync. So you can imagine that a DNS server is getting hit with DNS requests like thousands per second. So every request and reply will have a transaction ID attached to it, just so you sent out one with transaction ID 1 and coming back will be transaction ID 1. You could say, okay, that was the reply to this particular response, or that was the reply to this request. And there's a bunch of response codes you can see there. Hopefully we have response code 0, which is normal, but you'll see the next often one will be name doesn't exist, right? The response code 3, and we'll be able to look that up. So it's pretty easy in the filter dns.flags.response. And then we have other display filters that we can try in there. All right, so let's fire up Wireshark. So the way we'll do this is, let's move this hackpad over. So we're going to have Wireshark. I'm going to shrink Wireshark down a little bit. Something like that. And then I'm going to put my command line up here. So I'm going to do kind of a split screen deal. Yeah, it should be fine. All right. So with Wireshark open, we always go to capture options. And we find your particular interface. And we uncheck all this crap over here on the bottom right side. We don't need any of that. And we click start. Right? And you've got some packets going. So whenever you're testing out DNS inside of Wireshark, you have to be pinging names. You have to be trying to go to websites that you don't normally go to. We just went to CNN.com. It's in your DNS cache. If you type ping CNN.com again, it's probably not going to show up in Wireshark because you have it cached. So we need to be basically going to off-the-wall places that you guys normally don't go to. So with Wireshark running, capturing, we are going to try to find a website that you normally don't go to, and mensa.org. That's pretty cold-blooded, but yeah, I'm gonna bet that you guys don't normally go to mensa.org. Not putting you guys down, but this is not a very common website that normal people would go to. All right, so mensa.org. Let's try to think of another one that that you guys haven't been to. Let me think here. If you're a liberal, you probably don't go to Drudge Report very often. Well, if you're Asian, you've been to Hello Kitty, but I'm pretty sure I haven't been to Hello Kitty recently. So Hello Kitty. And let's pick another one just for kicks. Let's see here. NRA.org. Haven't visited that in the last 5 minutes. So, okay. All right, so you can just pick 4 spots that just think of some places to go to. Right? So we got that in there. We're going to click stop on our capture. And of course, we've got, I've got 55,000 packets in here. Quick filter will do. We'll just filter out for DNS, and it's just going to be DNS in the filter box, right? And of course, you've got tons and tons of stuff. How many of you have this LLMNR, Link Local Multicast Name Resolution? Okay, this is a Windows thing. Right, so you should see something in there, 224.00.252, and that one you can disable in your interface options if you want. It's completely fine. All right. So what you see here is all the DNS stuff, and you can see that the DNS queries are going from your IP, whatever it is. In my case, it's 183.39, and it's going to my DNS server, which is 172.18.2.2, right? And then the next packet coming back should be the reverse. It's going to be the reply coming from the DNS server back to you. So you have a query and a response. Very normal cadence happening there. If you you can scroll to the right and you see this all these hex numbers. Like I've got a 0xA360, 0xC221, 0x23C3. That is the ID. It keeps everything in order. And if you want, if you click on the query, and then you go down to the details here, down in this pane, the second half of the pane, you'll see domain name system. You can expand this out by clicking the plus sign. There you can see the transaction ID. You can see the flags, and the flags you can expand, right? And you see like 0 is a query, that's normal. 1 is recursion desired. Recursion desired. What recursion desired means is it's basically telling the DNS server, it's like, it's fine if you ask another DNS server. You may not know it, but it's cool if you ask someone else. Right? Because if no DNS server out there, or actually not very many DNS servers out there, will hold the entire DNS table for the entire internet, that would just be way too much information. So we have what's called root DNS servers that have, it's like has an A and a B and a C, and those hold humongous databases, but you generally don't go to those very often. You go to a subset of those servers, and then what happens is they will start caching the information. So we want to keep DNS queries down to kind of a manageable level. Right, so that's quite a bit of information contained in this stuff right here. Now, if you want to look up the DNS flags, an easy way rather than kind of clicking through all this, what you could do is you could do DNS contains, then you have to use quotes, and let's see if DNS contains CNN, if we get that. No, don't get that. Hello Kitty. DNS contains quote Hello Kitty quote. And we found the Hello Kitty DNS request. Looking at the flags, you could do DNS dot flags. Now, if you just do DNS.flags, you're going to basically come up with all the DNS because they all have flags in them. That's nothing too spectacular. But if you do DNS.flags.response and then double equals 0, you're going to get all the ones. These are all queries. They should all be queries here because the response code 0 is all queries. So this is a pretty easy way to find out what the guy was searching for. So right here, Numbnut here was searching for Mensa. He searched for Drudge, Hello Kitty, and NRA.org. Now the mail.google.com, I wouldn't worry about that because if you've got Gmail in the background, it's automatically going to check it. So that's not necessarily a live, what I call a manual search or a manual DNS query. Also right here, mscrl.microsoft.com. You did not type that in. You did not manually look for that. But you can probably guess by the name of what it does. So who can guess what CRL means? 50 points. Curl. Well, in some places it would mean curl. Control. Think security. I know someone out there knows. if you're going to a HTTPS website, what do you need to check first? Revocation list, there you go. So it's certificate revocation list. You're going to see if the SSL cert is good and hasn't been nuked yet. So very good. So that wasn't you checking. That was the browser or whatever your operating system automatically checking. Okay. Now we shouldn't have any that are response code 1 or 2 because I don't think we had any failures. Well, the one's going to be, let's see here. One's going to be the response. Okay, the flags. There we go. Actually, I think I have a typo in my hackpad. I think response code, I should have called that something else. Yeah. Okay, so you can see dns.flags.response double equals 1. All of these are queries. So 0 is a query response. 0 is a query, and 1 is the reply coming back. So standard query response, that's what happens when you just filter out flag dot response double equals 1. Right. So now let's start up another DNS request. Start another DNS request. We'll also restart our capture here. So we'll start our capture, continue without saving. So we've got some captures going. Also clear out your filter. And now what we'll do is we know that when we pinged Hello Kitty, it worked, right? And if you ping Hello Kitty again, when we search for this, hopefully when we go through this particular trace, we're not going to see any response or any response to our query. We shouldn't even see a query because everything is cached in our DNS cache, in our local cache. Right? So at some point that cache is going to time out, and if we ping Hello Kitty, we're gonna see it again. But what we're going to do is we're going to ping something at Hello Kitty. We're going to ping, let's say, www. Let's see if there's a www.hellokitty.com. Okay, so that dies out. Okay, we're trying to ping a non-existent entity out there. And if we ping www.1.cnn.com, let's see if something comes back. Okay, so they have a www1. And let's ping www.100.cnn.com. Okay, so that bombs out. So we're purposely trying to ping stuff at known places, but with a non-existing prefix in front, right? We're trying to go to a server that doesn't exist there. Okay, stop your capture. Okay, we're going to filter for DNS. And you can see it's a lot more bare. And if we scroll to the right, and I'll zoom in to help you guys out. So you can see the query still went out for www1 for Hello Kitty and CNN.com. So our computer still asked for it. Okay. But then on the query response, it's telling you, dude, there's no such name. Right? So if we want to look at the response itself, DNS flags dot response double equals 1. So that's all the responses. Okay. So standard query response, no name, no name, no name. It's basically the DNS server saying, no way. Now notice, if you look at where the response comes from, if you look at the source, did the response come from CNN.com or did it come from your local DNS server? Yep, the local DNS server is that guy that actually told you. So what happened here is when you pinged out for www1 whatever, you first hit your local DNS server. Your local DNS server kind of kicks you off to the other DNS server. It's the go-between. It hits CNN's DNS server, and then the reply comes back down, hits the local server, and then comes back to you. So that's why your local DNS server is the guy that's telling you, hey, I don't know anything about this. Or more appropriately, CNN.com told me to tell you that it does not exist. Right? And then if we want, we can expand this out. We'll click on any one of these, doesn't matter. You should only have 3 or so. If we look through the flags, let's see. Flag, you've got a 1, so response. Message is a response. Hold on for just a second.
All participants are muted.
All right. And can everyone still hear me? Okay, cool. Yeah, just another reminder for that headset. It's very important. Okay, so that flag under 1 means it's a response, so that's good. We've got a couple other flags, recursion desired, recursion available, all that good stuff. And answer. Down here you've got question, answer, authority. Right? Answer means a DNS server gave you the answer. Now where you see authority R, it means that the actual DNS server for that domain, so CNN.com's DNS server is the one that gave you that answer. Right? But in most cases, that's really not necessary. How many of you have had the pleasure of managing DNS? So either through Windows, crappy DNS server, or on Linux bind. Yeah, the Windows, it's all right. Anyone out there manage DNS through dynamic DNS like Dyn DNS? So you have a dynamic IP address for your home router, Verizon, DSL, cable modem, whatever, and you want to be able to hit it from anywhere on the internet. That's where you're going to be using dynamic DNS. That's how we're able to get our you can do your GNS3 labs. You could set up a GNS3 lab at home or set up a home lab of Cisco routers and be able to telnet to a domain name, and it'll hit your home no matter what IP it's changed to. So dyn.org. It used to be free. I don't know, have they started charging for it? Let's just see. And there's no IP. No IP got hit. They got into a little legal trouble because it was alleged that they were hiding botnets and stuff like that. So no IP is another dynamic DNS service. Don't know how good they are, but apparently they're pretty popular. So something to look into if you've got DSL or cable modem. All right. Okay, let's play around with some other filters. Let's see. You can filter out by the transaction ID. So it's pretty easy. DNS dot ID and double equals, and you'd have to know the ID. So in my particular one, I see that I've got a transaction ID 0x9AB7. And then if I do that, I should get the query and the response for that particular one. So that particular transaction ID was for my CNN www1.cnn.com transaction ID. Right? So you're going to get the query and response. Okay, and of course, as you notice, like with everything, if you didn't know the particular filter, when you type in DNS dot, you have all this stuff that you could scroll through to. The quadruple A, that's IPv6. All these other flags, a lot of them I have no clue about. There's just way too many flags in here. DNS ID we know. Got some keys, don't know about that. Yeah, there's just a tremendous amount of stuff here. Well, the ID must match. If if they don't match, it's not the same query. So that was the same question. If we're looking up this query 0x9ab7. That's on my screen, right? And I looked up CNN.com, www1cnn.com. The response comes back with the same transaction ID. That is the response to that query. That's how everything keeps in sync. It's the same as like a TCP sequence numbers. They have to kind of be in line. So it's the same idea. Or else what's going to happen is your computer is going to be going, okay, I got this reply back, but which query, who is that reply to? Like, I send out all these queries, I got this reply, which one is it? Now, as far as troubleshooting, what are you going to run into? You're going to run into typos. You mistype something. So, here we did like www100.cnn.com. It doesn't exist. You're going to get back that just basically, I don't know who that is. This name doesn't exist. Wrong DNS server entry. So you have the wrong DNS server. Usually this is not the case for most guys in here. That's a pretty egregious violation. If you manually put in your DNS server is 8.8.8.9, I'm going to guess that might not work. Maybe it will, I don't know. But let's assume it doesn't work. That's a pretty messed up way of finding that. And then the DNS server is dead. So common thing, sometimes DNS servers die. How do you troubleshoot? You put in 8.8.8.8, and usually that should be okay. Okay, transaction ID doesn't have any correlation with the client port number assigned by Windows or the UDP port. I don't think so. I don't think that port, I don't think it matches up to the port. But I mean, we can see. Okay, so let's see here. I'm looking at my particular query. If I open up user datagram protocol for that particular packet, I see that my port is 64,330. Yours will obviously be different. So what is that in hex? Well, let's find out. Let's see. We may find something here. 64,330. Of course, yours is whatever. So decimal. Now I'm going to change to. Okay, let me go to programmer here. There we go. Okay, I'm in decimal. 64,330. Change it to hex. No, completely different.
All participants are muted.
So looks like it's not related, at least on the surface. That's a good question though. Would be cool if it was related. Okay, let's see here. What else can we do? Generally, when your computer asks for a DNS name, 4 queries are going to be sent out. Now, the 4 queries aren't going to be sent out from your computer. It's generally going to be from the DNS server upstream to the other DNS server. So you're only going to see those 4 queries if it's a local DNS name that you're trying to find. Let's see if we can somehow get that to happen. So let's do this. Let's start our Wireshark capture again. Go back to your command line and let's ping something local. So ping Bob Hope with nothing. And I mean, if you get a reply back, I'll be very surprised. But okay, if you ping Bob Hope, nothing happens, right? Now let's go back to Wireshark, stop it, filter by DNS, and let's see what we got here. Yeah, I've got the, Dropbox query, LLMR. So that particular one didn't even go out using regular DNS. Windows did that. And if you guessed correctly, LLMNR is kind of the Windows successor to this old ugly ass protocol, NetBIOS NetBEUI. So back in the days, NetBIOS NetBEUI, you could, all computers have a computer name. Mine's called Humpster. If you ping Humpster, then it's going to get there. If you do / Humpster from another machine, assuming I give you the password and stuff, you will be able to go into my C drive and do cool stuff. It was this old protocol. It was cause of much fun in the NT4 Windows 2000 MCSE class days, where people figured out that, oh, I can do C $ and get into a guy's hard drive, then go to the desktop folder, copy files over and over, and cause the guy's desktop to fill up. Okay. So you can see on the LLMNR, if you have that turned on, the flags they look very similar. And it's basically a way of doing local DNS without a server. If you're running Dropbox, you probably see the Dropbox stuff. And this Dropbox stuff is local. When you run Dropbox, periodically your Dropbox is going to look on your local area network to find another guy that's running Dropbox. And if all the passwords are the same and all the information is the same, you'll start syncing up. So this works if you've got a laptop running Dropbox and you've got a tablet running Dropbox and you're on the same account. If you throw something in that Dropbox folder on the tablet, it's going to get updated locally onto your laptop. So it doesn't necessarily need to traverse the network on the internet again, because there's no point. If you slam a 100 meg file into that Dropbox, okay, yes, it's going to fly up to the internet initially, but then locally on the other computer, you don't need to download that 100 meg file from the internet. It'll just go computer to computer. Okay. So we weren't able to see the 4 queries, but your LLMNR, the new NetBIOS NetBUI, took that and did the query. Which is pretty cool. All right, and if you want to turn the LLMNR off, you can always go to your interface stuff. Don't do it now, but change adapter settings, wireless network, or local area network, depending on what it is. And if you scroll down, you've got this, I'll expand this out, link layer topology, discovery mapper, and discovery responder, that type of stuff. And then if you really don't need it, you can turn off the IPv6 to get rid of even more crap. And there's also another place that you want to go to is, see if I remember how to find it. There's this menu that says sharing. Let's see here. Yeah, so in here, sometimes you get that menu come up like home, private, public, all that good stuff, and sharing. I think it's, yeah, there we go. Advanced sharing settings, this network discovery stuff. You might want to turn a lot of this stuff off if you don't need it. Just be careful sometimes with this because you might break something just, if you're not careful clicking stuff. Because some people actually do want discovery turned on. And if you're ever not sure, do a Wireshark with the option turned on, stop the capture, then do a Wireshark with the option turned off. Then you can compare to see what extra traffic is being sent out. Okay, so that was it. We went really quickly through DNS. Any questions about DNS and Wireshark? It's pretty straightforward. The filters are easy to know. Looking at the queries and the responses is pretty cool. And you'll be surprised if you run a live Wireshark filtered out by DNS and just sit there. It is amazing what your computer will query for if you just let it sit there. And a sure way of finding out that your computer has a Trojan horse or a virus or a rootkit is you just see weird DNS queries going to just strange names. Right. Other than the Akamai and the normal stuff, you just see stuff going to just weird places. All right. Okay, how are we doing on time? We're at 50. Okay, we're doing pretty good. Not too bad. I think we'll get this. So ARP stuff, very cool, very nice. And actually what we can do is while we're talking about ARP, we can start a capture. Let's go to capture and options. And the reason we can start a capture without blowing stuff up is, remember a couple weeks ago we had capture filter. And what a capture filter is we can choose just to capture this stuff. Right? So inside capture filter we'll do that. And we'll find your network connection. So mine is wireless. And on this particular one, we can update list of packets in real time. That should be okay, because all we're doing is we're capturing for ARP. And then click Start. Okay, and just we'll watch it go. So we have a question. How can we find if there is a delay in DNS response? Okay, good question. So there will be a little bit of delay in DNS response if it's DNS coming from outside your network. Right? So if it's DNS coming from inside your network, it'll be fast. But the way to do that is you want to add a column for time delta, so time from previous packet. And the way to do that is edit, preferences, edit, preferences. You'll have user interface and columns. And what we're going to do is we've got we'll have we'll add one. And you've got a drop-down menu here. And there's going to be a time delta here. Delta time, display, delta time conversation, and delta time. Any one of these will work. Delta time. And then for title, you could just say time since last packet or something like that. And then click OK. And it's going to add a column. In my case, over here at the very end, I'm just going to drag it to the front. Not to the front, but I'll drag it kind of sort of near the front. And this way, I'll be able to see the delta. So number of seconds since the last packet. So the way this works is you're going to get a query and you're going to get a response, right? You're going to be looking at these two packets, and if you have the time coming back from the response at let's say it's like, I don't know, 2 seconds, that might be a cause for concern. You know, if it's something like less than 2 seconds, I wouldn't worry about it. You know, maybe the DNS server is busy or whatever. But 2 seconds, more than 2 seconds, I would be concerned. Right. The Wireshark book does talk about one case where DNS is really slow, and the reason for that is they made their primary DNS server something that was off-site. So if you make your primary DNS server 8.8.8.8, whoa. So primary DNS server, all 8s. Okay. This usually is going to be up, but it'll probably be much slower than if you use a local DNS, because the query and the response has to go all the way up to Google and come back down. I mean, it'll work, but might be better to use 192.168.1.1 if that's like your Linksys router. It is kind of funny when you like troubleshoot client networks. If you're a consultant or something, you go DNS and you see all 8s. It's like, really? It's like you didn't set that guy back to the normal one. Okay. All right. So your ARP should be going. Lots of ARPs, right? Fairly busy. And you should see like, who has this? Who has this? Who has this? And what you should see is ARPs for the gateway. So in my case it's 182.1. In your case it's like 192.168.1.1, 10.1.1.1, something like that, right? So you should see ARPs for the gateway, and that's coming from your computer. So constantly your computer is going, hey, who's the gateway? Who's the gateway? Right? And also the gateway is probably ARPing for you. Hey, who's this? Who's .39? Who's this guy? Right? And then you should also see the replies like, hey, I'm .39 and my MAC address is this. Okay, so that's all ARP. If we take a look at these, you can just open any one of these. Click on any one where the info says, who has this? Who has? And then you expand out the address resolution protocol down here. I'll expand that out and zoom in. you can see that this is, so it's Ethernet. You got a protocol size. We have a sender MAC, sender IP address, target MAC, target IP address. Now when you see a target MAC of all zeros, that's basically saying, okay, I don't know the MAC address of this IP I'm trying to get to. I'm trying to get to .39, but I don't know the MAC address. Can someone please tell me? So that is a request. And then it gives its own MAC address, the sender's MAC address. And the opcode there, request 1. Now we have these other ARP. We've got, so instead of the whoas, you'll see this IP address is at so-and-so. Right? This IP address is at this. This IP address is that. That's a reply. And we can look and expand this out. You should see opcode reply. That's a 2. That's a reply. And it says, all right, my IP address, .39, and my MAC address, DC:85 DE, blah, 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 right? And the target MAC and target IP is the guy you're replying to. So what's cool about this is if you don't know what particular device that is, so let's say you're seeing ARPs from a guy and you're like, okay, I see the IP address, I see a MAC address. What kind of computer is that? Well, if you ever are trying to find MAC addresses, I do this every day here because I'm tracking stuff down. But coffer MAC address. So if you just Google for coffer MAC address or coffer, it's coffer.com. Is this guy who runs a free MAC address database. You can paste in a MAC address and it will usually spit back a vendor. Usually, right? So you find a MAC address, you paste it in there, you click that string, and then it'll spit back Apple, it'll spit back Dell, Samsung, so on. Very common. Coffer.com, one of the greatest websites for a sysadmin network admin. All right, let's go back to Wireshark. Okay, 60 minutes, good. Thank you for the reminder. Move this over. Yeah, I'm kind of liking the Fuse chat on the Samsung Android tablets. It's not too bad. Okay, let's see if we can filter out. We know we could filter out for ARP. There's kind of no point in this particular capture because we have a capture filter for ARP. So the only thing we get is ARP. There's nothing else in this capture. But we can filter out for opcodes. And I think if we do ARP dot, you can see like destination, hardware address, we got all this stuff. I bet you if you scroll down here, yeah, ARP.opcode, and I bet if we do double equals 1, we're going to get back all the queries. So all the who is. I'm going to zoom in a bit on here. There we go. So who has this? Who has this? So arp.opcode double equals 1. So that's all the requests. And you guessed it, if I change the filter to double equals 2, I should get all the replies. There's some other ARP codes out there for like reverse ARP and stuff like that. I don't think we should have any of those not very common use cases. right? So ARP code 1 works, ARP code 2 works. If you want to do the hex version of that works as well. So if you want to do 0x001, it's the same thing, but as you know, as you just saw, 1 works just fine. Okay, common problems on this one. Wrong subnet is a very, very common problem. More common than you think. Where does this happen? On the client configuration, someone's learning Microsoft or whatever. They're configuring a bunch of computers. They go down here to the network interfaces. They go into the adapter settings, IP address. They're manually setting IP addresses at home or whatever. And 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 I'm not going to do this, but you over here, subnet mask. You mess up the subnet mask. You make it a /8 instead of a /24. So what's going to happen here is you're going to ARP. You're going to ARP for everything, and your router is going to go. What are you talking about? Why are you ARPing for that guy? It makes no sense. They're not on the same network. You're going to ARP for the stuff that's on the same network. And the router will generally kill it unless you're running something called proxy ARP. And proxy ARP, the router is going to answer for you. Okay. Gratuitous ARP. Yeah, gratuitous ARP. So how many of you have, you're running a Windows network, you're administrating a Windows network, and you see something in the bottom right-hand corner, there is another computer with a duplicate IP. Duplicate IP detected. Right? Has anyone seen that on their network? Well, sometimes happens when you plug and unplug, computers in rapid succession. Duplicate IP. And the way this works is when you plug the computer in, you get the IP from a DNS server. Generally, your computer is going to tell the whole world, hey, my IP address is this, and my MAC address is this. It's going to send it a couple times. And then what's going to happen is a computer on the other end of the link is going to say, now wait a second, I have that IP address too. And that's where you get that pop-up in the bottom right-hand corner. That announcement is called a gratuitous ARP. Gratuitous ARP. It's basically telling everyone, hey, update your ARP table. And gratuitous ARP, as you could probably guess, can be used for nefarious purposes. How to search on the info column. This info column, so this is what Wireshark is translating it into. Okay. Because if you click on any of these where it has the info column, if you look down here into the actual ARP packet, it's not going to say what's in the info column. What you actually want to filter on is IP address, stuff like that. So let's see what we could do here. Okay, ARP dot. If we go down here, so filter by protocol, destination, hardware size, ARP code size, all this good stuff, right? So you'd be looking for, let's say, destination.hw double equals something. So ARP dot destination.hw double equals, and then whatever the hardware address is. Right? So this info is what is not in the packet. It's not like a data portion. This is what Wireshark is translating into. It looks at the ARP packet, it sees this target address, it popped a who has in front of it, and this tell, it looked down here and says, okay, there's a 39 down here. So it's just making it translating into a more readable format. In some other packets, in a lot of other packets, the info column is actually the data portion of it. So if you want to filter by IP address, easiest way, open one of these packets, go down here to sender IP. So let's say everything coming from my computer is IP. So 183.39. I right click that, apply as filter, selected, and it's going to put in here arp dot source proto underscore IPv4 double equals that IP address. That's probably the closest that you're gonna get to filtering on the info column. So everything coming from my IP address. Okay. Now what you usually want to do when you're looking at ARP, you want to look at everything that's not your MAC address. So everything not my MAC address. What you're going to do for that is you're going to find a packet with your IP address. So I know mine is 183.39. I know my MAC address is 4A:49. Right click your MAC address, apply as filter, and you're going to say not selected. So give me everything where the source is not my IP address. Okay, so in my case, this is everything is just going to be my gateway that's ARPing. If you're on wireless, the Wireshark and wireless is not picking up everything, and that's by design. You may want to look at getting a dedicated wireless capture card called Air PCAP, now owned by Riverbed. And it's kind of pricey. It's especially if you get the, I wonder if the 802.11ac has come out, but the Air PCAP cards are kind of pricey, but this is really what you want if you're going to be scanning, doing Wireshark on wireless networks. Let's see, buy now. Yeah, so the N adapter, don't even bother buying the B and G because, man, it's hopefully no one's on B, and G is kind of getting out there. So we have the NX, which is the 802.11a, B, G, and N. 700. Man, it's a little expensive. So $700. Get your company to pay for it. That's price gouging right there. All right, guys. Any questions about ARP inside of Wireshark? I think we're pretty much right on time.